Thank you, Anthony, and welcome everyone. Thank you for coming along to hear about our geophysics journey. What I want to highlight first of all is I recently was at a presentation by Professor Marnie Hughes-Warrington, and she described a new term she'd come up with called a technic, which is a person belonging to a subculture associated with technology. So I think we're all a little bit technic now. We've all gone through, we've all got our devices, many devices. We all want everything, all information at our fingertips. And I think this is a really important point because we need to recognise the changing digital landscape. We need to recognise the increasing digital ability of our stakeholders and the people who use our data, including internally at Geoscience Australia. And this is what this story is really about, is actually taking a piece of data and working it through the full pipeline and seeing what we get out the end. So why are we here? Well, I'm going to talk a little bit about the National Geophysical Collection. I'm going to talk about open data a little bit. I'm going to describe and give some definitions of big data and how I define big data and what we're trying to do with that at Geoscience Australia. I'm going to talk a little bit about machine-to-machine interoperability and specifically the fair data principles, and I'll go to that in detail later, but how we can make our data findable, accessible, interoperable and reusable. And then I'll talk a little bit and show you some demonstrations about the future for future data platforms to enable science. So first of all, I'd like to make some acknowledgements. I championed this work. I could argue that might have been my idea a long time ago, but Ross Brody and I can argue over that. But really, it was a contribution from a massive amount of efforts, and my Googling didn't manage to enable me to come up with photos of everyone. But the team was massive, and I apologise if I've left anyone off, but there were small contributions, large contributions, and this is the team that really made this all happen. There was also contributions from a number of organisations, either by in-kind support or financially through funding. For example, the RDS and Ozscope, Nectar and ANS funded some of the virtual laboratory work. And CSIRO helped contribute to building our virtual laboratories and helping us test and use the data. So, let's imagine what the future is going to be. How do we want to work? How do we want to be using the data? We're all going to be sitting, actually it's getting quite nice the weather, not today, but I want to be sitting out in the backyard watching the kids play around, having my Surface Pro on my lap and be able to check the data. I want to be able to see who's using the data. I want to be able to play around like I'm not really in a technical position anymore, but Alex Ip's going to all-out efforts to make it so that I have the ability to still do some geophysical programming on my laptop. So we want data at our fingertips virtually. We want the data available for students, the next generation coming through. We want to educate them, we want to enable them to use it. We want data available for industry. That's core to what we do at Geoscience Australia, and we want to make sure that we make the data available for them in a way that they can use it. We want data available for researchers. We want to enable it so we can have some amazing innovations happen on our data, and who knows what we're going to get out. We really want the data available for everyone. And if I get back to my original point of techniques, we've got people on their phones with Google Maps downloading all sorts of data sets now. We've got the grey nomads wandering around the bush wanting to know what rock type they're going, they're crossing. So we've got to really make the data accessible. So in this future imagined state, new data is collected from ground stations, sensors, mobile phones, drones, planes, satellites, and seamlessly added through to our data collections. All data can be seamlessly incorporated into the work that we're doing. And we want to be able to find the data and use it in any choice of platform or software, so we can grab the data and use it how we want to use it. So this is the future. So there we are sitting, that's me sitting out in the backyard with my Surface Pro, with my with my screen, which is a virtual screen running to anywhere. We're accessing the data sets, and then we're enabling them so we can do lots of fun stuff with the machine learning, implicit modelling in 3D, data analytics. Now I'm going to argue that the future is here, almost. We've already got interactive portals. This is an example of the AusGym portal where we can actually interrogate. We've got an ever-growing amount of machine-readable web services being delivered out of this portal from across state jurisdictions to enable the display and interrogation of those data sets in that portal. We've got virtual laboratories, so this is a screen capture of the Australian National Virtual Geophysics Laboratory, which I'll talk about a little bit later, where we're enabling the ability to find data sets, geophysical data sets, and then run some automated workflows using open source software on them. But we've also got the NCI's virtual desktop. So this is the NCI's VDI environment where we can actually run Jupyter notebooks, QGIS, accessing the data on the NCI, but also accessing other data sets available elsewhere via web services. So I promised you in my abstract that I'd talk a little bit about buzzwords. So we're going to go back to the definitions now before I go on to explain the work in more detail. So let's look at big data. So the Oxford Dictionary talks about big data being extremely large data sets that may be analysed computationally to reveal patterns, trends and associations, especially related to human behaviour and interactions. So much IT investment is going towards managing and maintaining big data. Now, this is all right, except for I don't like the human behaviour and interactions part. So as we do on Google, we find another definition. So I went to Wikipedia. So Wikipedia describes big data. It's a term for data sets that are so large or complex that traditional data processing application software is inadequate to deal with them. Big data challenges include capturing data, data storage, data analysis, search, sharing, transfer, visualization, the list goes on. So I like this definition better because this is what we're facing at GA, right? Our data sets are getting more large. They're not necessarily about human behaviour and interactions, but they're getting large that we can't deal with them in our traditional means. We can no longer, generate the magnetic map of Australia on a desktop like was done previously years ago. So this is what led us to the journey to go to the National Computational Infrastructure in the beginning. How are we enabling us to use these large data sets to create our large products? So we're going to continue on with some more definitions. So I also want to explain structured data versus unstructured data. So structured data refers to any data that resides in a fixed form. So this includes data that could be in relational databases, spreadsheets, and other structured data types. Unstructured data is stuff that doesn't reside in traditional row column data sets. So here's a little bit of a diagram. We've got structured data, which could be databases, spatial data, spreadsheets. And then we've got unstructured data, text, images or video. And the reason why I emphasise this is a lot of big data talk out there is about unstructured data. It's about how can we grab all these images, how can we grab social media and we can deal with that, right? And those are some big challenges. But Geoscience Australia, we've got very structured data. We know a lot about our data. We know what the metadata should be, and in most cases we have good metadata. And we need to be able to leverage off that. So rather than going down the route of unstructured data and trying to do too much, let's leverage off the structure that we already have in our data and the way we do our science. So then I'm also going to define semantic web. So semantic web is an extension of the World Wide Web through standards by the World Wide Web Consortium. The standards promote common data frameworks and exchange protocols on the web. So the semantic web is really describing the web as a data model. Then we have linked data, right? And linked data is actually how we're enabling the semantic web, how we're using the semantic web ontologies to actually build linked data concepts into our data at Geoscience Australia. So linked data is the term used to describe a method of exposing and connecting data on the web from different sources. Currently the web uses hypertext links. That's a very simplistic form of linked data, and I'll talk about more complex forms that we're using at Geoscience Australia later. And then ontologies. Now it's really important that we get our ontologies right. And I've had a steep learning curve in scientific data, getting all these terminologies right and getting it right in my head and being able to talk the talk. But I think we've really got to be structured about getting our formal naming conventions and definitions of types, properties, interrelationships of these data, and this relates to that structured data. So here's an example. So over on the left here, so this is Geoscience Australia's public data model. So this is our data model for how we're describing the way that we're publishing our data out to the web. So we have, I'll use the mouse here. So we have our catalogue, right? So this is the list of all of our data sets, and we have our ECAT catalogue, which lists all of these. Now in these we have data sets, we have web services, but we also could have samples and surveys, and this will be expanded as we develop more types of data, or we expand into more areas. And the semantic web is the model for how we describe it, and linked data is how we are sharing it and getting people to use the data. And so it's really important that we understand the ontology, we understand the semantics to be able to maximise the way we are using our metadata and describing it. So what does this have to do with what we do with data at GA? You know, GA data is open, you can download it, you can sort of find it if you can. So we do have a great catalogue, don't get me wrong, I have a fantastic team that's built our catalogue, but the catalogue is only as good as the data that's in the catalogue and the metadata. Why isn't current practice good enough? So we can use our data at the moment, if you know how to use it, if you have the right software, and it also helps with the National Geophysical Collection if you actually got a geophysicist on hand to grab to do it. All right, so yes, GA is doing a really good job, and we've done a really good job in the past, but it just isn't getting us that next step further. How do we measure how we're doing with our data internationally in the informatics community? What is the international community doing? And I'll give you a little definition there. Geoinformatics is the science of and technology which develops and uses information science infrastructure to address the problems of geography, cartography, geosciences and related branches of science and engineering. So we're really pulling from the international geoinformatics community at GA with our partners at the National Computational Infrastructure helping us to really make sure we're doing best practice to enable our data. So how do we measure how we're going? Well, I talked about the FAIR data principles initially in my introduction. So this is, these data principles were drafted by the Force 11 group, which is a consortium, a community, international community of scholars, archivists, librarians that have come together, and they actually want to enable best practice with data sharing and knowledge via information technology. And so they've come up with FAIR data principles. So they're saying that our data should be findable, accessible, interoperable and reusable. My slides will catch up with me. So the principles have since received worldwide recognition as a useful framework for thinking about sharing data in a way that will enable maximum use and reuse. And the Australian National Data Service have guidelines that set out some broad principles. There are some really detailed principles that Force 11 puts out, but I'm just going to talk about the broad principles today. And I'm going to talk about how it relates to what we're doing at Geoscience Australia and how we're using that to enable the geophysical data collection. So findable means that we need to make sure our data is findable. All right, so that means it has to have rich metadata. It has to have a handle or digital object identifier, a persistent identifier via the internet. So we have our data is findable. We have GA data publications and catalogue, or ECAT, and here's a screen capture here. And we can see we have various keywords, we can search through the metadata. It's only as good as the rich metadata within it though. And here's an example, and I've just shown it small, but this is the sort of rich metadata that I'm talking about. This is, we use ISO 19115 as our metadata standard, and we can see that there's a number, we have then our own GA profile for this, and a number of fields, for example, and you can't see, but this is lineage, this is where's the data come from, an abstract describing the data, we've got keywords to make us be able to find the data. Where is the data geographically located? All of these things are important because these are delivered in a machine-to-machine readable way so that we can then search them, machines can search them and find them. Accessible. Well, we want to make sure the data is accessible and open where it can be. And we're lucky at Geoscience Australia where 95% of our data is open, and we have a CC BY licence across all of our data sets. But we also need to consider in accessibility is the push by the Federal Government of Australia for open data. And so here I've got a link through to the PMNC's Open Data Agenda, and we've also got data.gov.au. Interoperable, what does that mean? Well, it means we have to have agreed community formats, language and vocabularies. We need to have agreed standards. And now this means that Geoscience Australia is participating in a number of international organisations so that we can make sure that all of our data is to open agreed standards. And examples of that are One Geology, where we've actually contributed to the World Geological Map by using open web standards. And then reusable. So reusable at the end, this is a tricky one. We want to make sure our data has enough richness in it that it can be reused again. So that means we need to have clear machine readable licenses so that we know that the data can be used again, but also provenance and information about that data. So you don't need a geophysicist sitting next to you to actually help you use that data. You can grab it and you've got enough rich metadata to understand what that data is. Okay, so now I've gone through all the definitions and we're almost halfway through the talk. Now let's look about, okay, what we've done with the geophysical data collection. So what is the geophysical data collection? So GA is custodian of about 300 plus terabytes of geophysics data. Now this is from us being curators of our own data sets, but also our partners in our state and territory geological surveys. Now this data consists of seismic data, reflection, passive refraction, magnetotellurics, airborne electromagnetics, gravity, radiometrics and magnetics. Now what we did focus on was we realised that we needed to reduce the National Geophysical products with increasing resolution, which led us to investigate the National Computational Infrastructure initially. Noting that when we first started this journey, cloud costs were inhibitive for us to go to commercial cloud, and we could argue they're still inhibitive in some aspects. So we needed to work out how can we leverage off this large data collection. Now we were lucky enough at the time that the research data, or it was RDSI then, came up with some grants. This was a NCREST funded infrastructure to actually enable to deliver significant data sets to the Australian research community. And the Australian National Geophysical Collection was identified as one of those. And what's important to note here though is we decided we couldn't do everything. Let's just focus on a few data sets to begin with. And we focused on gravity, magnetics and radiometrics. And so that totaled about 30 terabytes of data. So still very much in the big data space. You know, too hard for us to work with this data on an individual PC with traditional software packages that we use. So we really needed to partner with the NCI on this. So let's talk a little bit about the NCI. So the NCI have their National Environmental Research Data Interoperability Platform. All right, so where they're actually trying to make data available, they want to provide data. They are providing data storage infrastructure, data discovery standards and conventions, data access and services, so that the data can be accessed via virtual labs, catalogues and portals. And they actually have their own virtual desktop infrastructure, the VDI, that we can use. And here's a Leslie Wybornogram of the National Environmental Research Data Interoperability Platform, NERDIP. And we can actually see here that we've got geophysics named. We've got airborne geophysics sitting here, and it talks about the different layers. So this is the storage sitting underneath. This is the standards layer. We've got conventions on this is the API layer. We've got standards conventions on the top, and then we're delivering them out via services. And then there's various tools that want to have access to these. And we can also see that we've got the VGL, the Virtual Geophysics Laboratory, in there as well. And also on the AusScope portal and data.gov.au. So we wanted to be able to get to the point where we could deliver our data in the way that the NCI saw that the data could be delivered through these layers. So what did we start with? Well, we started with our open data, so licensing, accessibility, that was great, but it was big. We had good data management, but it was siloed. We had a relatively good data delivery system, but it was siloed and it wasn't machine-to-machine readable. It was still using community exchange formats, and it wasn't scalable, and it definitely wasn't interoperable. There were lots of proprietary software and formats out there that the geophysical community uses, and none of them we could really use in this open way that we wanted to do. And there was a reliance on proprietary codes and desktop software. So we needed to work out how to bring the codes to the data, and we needed to work out how to enable access to new codes on this data. So metadata. Okay, so in order to make our data interoperable, in order to make it available and accessible, we need to have that rich metadata. We need to have it in a way that the user understands what that data set is. Now we had pretty good metadata in the geophysics datasets. It was just siloed again. It was in lots of different ways. It was a bit hit and miss, the discovery. So we needed to work out how to do that. And this is where the multidisciplinary collaboration between all the teams worked, because we had me being the geophysicist saying, oh, but this is the important data over here. We had, Jingbo and Irina Bastrakova saying, but this is the discoverability metadata. This is important. And then we had Claire and Ben and Leslie and Kelsey saying, but this is important for us to be able to deliver it to the standards that we need for interoperability for the climate convention. So we had lots of tossing and turning, and we needed to work through that. So we needed a robust, flexible means to associate the data that we did know with authoritative metadata. We needed to make the data available in an interoperable, self-describing, machine-to-machine readable way. I keep saying all those buzzwords, but it's so important. And there were a few options. So the one option that we decided on was, well, HGF5. That's what they're using at the NCI. Let's look at HGF5. How can we use, HGF5? It's self-describing, it's flexible, it's efficient, scalable. So let's go with that. It's not really interoperable. All right, so let's go with NetCF4. It's simple, standardized, proven. We can work with that. Nope, it's not fully interoperable. Okay, so let's go with fully CF compliant NetCDF data, which is highly interoperable. It's got an extensive tool set available and a community that is supporting that standard. And so that was what we decided, that we needed to make sure our data was NetCDF CF compliant. Wow, so that was pretty tricky. But what we ended up doing was we managed to losslessly translate the geophysical data, so this is just the data, I'm not talking about the metadata yet, from legacy formats into the NetCDF. The data structure supports proven web services, so we have already delivered test data via OpenDAP into environments including IPython, which is now Jupyter Notebooks and MATLAB. The gridded geophysical data was really straightforward. Many similar examples from climate science and Earth observation, so we went with the gridded data first. Non-gridded data, which is the line data or the point data, the data attributes are represented in arrays sharing at least one common index, and NetCDF4 HDF5 also allows us to represent multi-dimensional data. So we could actually have time-based data sets like airborne EM, which has multiple time-based windows for the one geographical location. But the quality assurance of the metadata was tedious but vital to success, because in order for us to get that CF compliance, we had to get the metadata into the files. And so here's an example of one of the NetCDF files. It's a gravity data set. And so you can see here, if you can zoom in, that there's the traditional channels that we're used to seeing. Actually, this is MAG. The channels that we're used to seeing inside of a magnetic Intrepid database, which is the traditional way that us geophysicists would process the data. And we're actually transforming that into a NetCDF format. And then we're having inside the header, we're having rich metadata inside the header. So you can see some examples of that metadata down here, where we've got license, keywords, institution, and metadata links. But metadata was tricky. I was still complaining, hey, you're not getting the metadata that the geophysicist needs. I want to know what the line spacing is. I want to know what the year of the survey is. I want to know who collected the data, so which was the instrument used, all of that sort of stuff. That we couldn't cram into the NetCDF header. But we did have that information. I can see Claire smoking in the corner there, laughing because she remembers the meetings. So we had the data at GA. We had it in a database. So this is us whiteboarding. There's lots of whiteboarding happened about us trying to understand what we were trying to do. So we did have this fantastic Oracle database, our geophysical surveys database, that had all of the metadata that we need, all of this stuff that I thought was important, and my fellow geophysicists, that we needed to put with the data. And that was what was being used to deliver the data out of GADS. How can we make that available? So we pushed some of it into ECAT. We tried to cram some of it into the ISO 19115 records, but that kind of wasn't good enough. And then this is also showing how then we're also synchronising the data over to NCI, how we're going to make that data, because the data's sitting over at NCI, how we're then also going to link that through to all of those data sets. We also had traditional ERS data sets as well as the new NetCDF data sets. And then we also, externally to make it more complex, we also had our ECAT sitting out in Amazon as well. So we had multiple environments we were trying to jumble between. So this is really showing that metadata, the interoperability between different systems, using proper web service standards to actually cross between all these systems. And in tiny thing in here we can see linked data, right? Where we actually worked out that we could put the geophysical data, actually I don't work out, Nick and Alex worked out, we could put the geophysical, the rich scientific metadata for the geophysical data out as a linked data API directly from the database, and that could be linked into the NetCDF header to enable us to have the best of both worlds. We've got a standards compliant NetCDF CF data set, and we've got the rich scientific metadata. But then we got into more problems. We've got one geophysical collection, but we've got multiple surveys, right? So when I define a survey, that's a campaign where a plane went out and collected an area of data. And in that, usually they collect magnetics and radiometrics and probably and DEM as well in that one survey. And on top of that, there'd be multiple radiometric surveys. So there's at least 4, usually more, data sets related to one survey. And then we've got those multiple surveys related to the data collection. And then we've got multiple types of data sets, because we'd have our line data as well as we'd have a gridded data set come from that. So this is where, I thought I'd had it. This is where getting the ontology and the semantic web and having a linked data expert at your fingertips really came into its own, because we realised when you actually try and lay it out in a model and draw it out that it doesn't make sense. Okay? So this didn't make sense. We couldn't have 2 surveys coming from the one data set, all right? Because the surveys created the data set. So then we realised we have this collection, all right, which is our geophysical collection, which is a data set in itself. And then that's split down into multiple surveys, which are data sets, and they're defined by an activity, which is the survey. Okay, so this is the actual data, the green, and the blue is an activity. And it's really important to get that ontology right. So we came up with a way to do it. So even though metadata was everywhere, we had our Oracle database inside the GA building, but we managed to push metadata out from that, a bit of metadata out from that, into our data catalogues to make the data discoverable. So this is ECAT, our GA data catalogues. We then managed to push, as a bonus, push that metadata out to a number of different other catalogues as well, data.gov.au, Research Data Australia's catalogue, which is the ANZ catalogue, AusGen, but also over to the NCI's data catalogue, which then sat on top of the NERDIC platform, of which the geophysical data, the Geophysical National Collection is one of those data sets. And so this was really easy to demonstrate straight away. Here's a picture of the NCI data catalogue, and you can see there's the Australian National Geophysical Data Collection described in there, which is being harvested from our catalogue. We've also got the AusGen portal, and we can see here's a older geophysical service, but that's being pulled from GA's data catalogue, ECAT. But what about the linked data component? Because we still wanted that rich data about the survey. So here's our API coming out into the big worldwide wonder of the web. But what does that mean? So what's important to understand with linked data is it's not just the human readable, right? So we want to present this. So here is an example of an API landing page for our survey. So this is the Chevron Geophysics conducted this survey. It was mag, radiometrics and elevation. It was, the ID is 850, so it was survey number 850, and that's a description of the survey. And the information goes on. It was collected in 1999. So this is the human readable format, but it's also machine readable. So this is being put out so that it can be harvested by JSON, Turtle, XML, RDF, all these things that I know nothing about. But the machines can grab it in various formats, this same metadata which we see as human readable, and which means that the bots control the web and find the data that they need. And they can find it based on that rich data set. So someone could go out there and say, well, I want to know, how many surveys Chevron Geophysics did for Geoscience Australia, and they could go and find that information. So, we've got the data available now. It's available, it's got its rich metadata, so what are we going to do with it? So, we've already got it available in the Australian National Geophysics, Virtual Geophysics Laboratory. So here's an example of the isostatic corrected regional gravity of one of the national maps. But then we can also zoom in here where I'm actually showing an outline of a Leonora magnetic survey data set overlain on, I'm showing the Leonora radiometrics data set overlain on the gravity, and we're also, it's also overlain on the National Radiometrics Survey as well. So we can actually load a number of different surveys. We can interrogate over here on the left. We can see we can put in keywords, and that'll search through, that metadata that ECAT is putting out, which is called a CSW, and find the information so that we can we can actually display those data sets in the Virtual Geophysics Laboratory. So then we can do things like, here's an example of a joint inversion of magnetics and gravity data done using eScript. And I've just did a bit of an example down there. So that ran, I don't actually know the size of that survey, but it was a quick inversion and ran for less than 2 hours at a cost of less than $4 on Amazon in the national, in ANVGL. And to demonstrate interoperability, last week I emailed my colleagues in DEA and said, hey, you guys were interested in the radiometrics data for it, weren't you? And so they'd already demonstrated, then Simon Oliver, I don't know whether he's here, he said he'd already demonstrated that he could grab it in, but he updated the endpoints and could grab it in and pull out for me an image of some of the radiometric data sets straight out of the data cube instantly using a bunch of script. And that's actually the same area that I was also playing with in ANVGL, Leonora. So we've actually shown that, yes, we've been aiming towards ultimately being able to use it in the Australian National Virtual Geophysics Laboratory. That's why we really wanted to enable the data to begin with, but it's actually enabled. It means that a DEA can now access these data sets, and the radiometrics is really, that surface information is really important for the environmental science that they do in that area. So what are the geophysical challenges that we want to try and tackle with the data now? So Peter Milligan laid down the gauntlet for me when he retired a number of years ago. Now he used to, lead the projects that used to generate the national coverages of magnetic maps of Australia. And these were done by a grid merge. So here's an example of pulling out all of the individual magnetic national government collected magnetic surveys. And so this is actually pulling that out of that CSW, the linked data information, so that you can get the coordinates of all of the surveys and display it on a map. So these were all individually gridded and then merged together. So we were doing it at the NCI, we were merging all the grids together at the NCI. But I was always cautious, because when I was an exploration geophysicist, I wouldn't use the national map, I wouldn't use the national collection, I'd actually grab all the individual surveys myself, because if you go down right into the detail where the explorers are looking, they're interested, and often their tenements or the region that they're interested crosses multiple surveys. And if you look right down in the detail of the national maps, or the national mag map, there was, little edge effects. The resolution wasn't as good as it could be, because it's kind of had to average the resolution across the coverage. Looks great on a national poster. It looks great on a banner outside in the hallway, but as a geophysicist in industry using that, no, they want the data, right? And they want the data, and they want it easily. And often what I'd have to do is I'd have to download the 5 data sets, load them into my proprietary software, grid them all up myself, and then do all my work that I needed to do. So could we enable the line data sets, the survey data now that we've got over at the NCI, so that we can generate this magnetic map, maybe on the fly as needed, or the whole thing from the line data? So yes, we can. So the team's been working very hard over the last couple of weeks to actually show this in a Jupyter notebook. All right, so this, I'm going to walk you through a demonstration. We haven't refined the scientific geophysics gridding and stuff, but it's a demonstration that we can do this, right? And this is something that we can put out publicly. We could actually package this up in a user interface, but we could just put this code out there and to the stakeholders and say, hey, this is how you get to the data directly. And so this is an example. So here, obviously there's it's in Python. This is in Jupyter Notebooks. This is working on the VDI at the NCI. But this could be run, because these web services are being delivered into the web, this could be done anywhere. Anyone with Python on their laptop or working in AWS could pull in these services to do this work. So we've got some bounds. So I'm looking in Leonora, that was my old stomping ground. We're looking at some keywords, which this is pulling it straight out of the harvested CSW, so the catalogue web service. So we want to make sure it's geophysics data, we want to make sure it's digital, we want to make sure it's magnetics, we want the line data, and we want AWACS because we want the levelled mag data. And I don't want anything older than 1990, so we'll just grab that data. And it gives me a printout, we show you. Okay, so we've got a whole data set. So it's picked up, if anyone knows the area, it's picked up some Menzies data, some Leonora data, some sandstone data. James could probably know all these and rattle them off as well. All of the data sets around that Leonora area. So it's picked them up, and we can see these are still individual files. So it's picked up these are the project numbers, that P1260, P1596. That doesn't mean a lot, but in that linked data catalogue, we can pull out information about them. So let's try and, I've taken that slide out, but we can then print, okay, well let's print the metadata, let's actually check what we've got, what's the names and things like that. So now we want to retrieve all the points. So this line of code is just getting all the points in that data set. So it's in the points in the line data and pulling it together into one data set. And so this is an example of the types of points that it saw, right? So it pulled out some really old data sets. So this was before we filtered for the 1990, so this is a really old data set that's looking a bit wheelie. Apparently it was digitised. There's some pretty good data sets. We can see the inlines and the cross lines, and there's a data set that was collected on an angle. So now we can grid the points, and we can come up with a grid of that data being pulled out. So this is full end-to-end, like I've showed you the steps, but this is full end-to-end processing from discovery all the way through to product of delivering a magnetic grid to the resolution that you decide in your gridding of Leonora. So we can see those well-known structures around the top of Leonora there. So hot off the press, wow, we've got Leonora region magnetic grid directly from the line data, directly from web services that are machine-to-machine readable, coming off the NCI in standards compliant data. And I'd like to acknowledge Alex and Ross and Yvette for working on that the last couple of days to get that all working. And so we can see, we're so close, we're there. We could sit out there, you could sit anywhere, you could be running a Python notebook in Amazon that's grabbing these services, so you could be sitting out in a container ship at Leonora, or a container at Leonora and working. You could be at a university, you could be at Geoscience Australia and actually using this data and creating these automated end-to-end processing workflows. And so just to check, this is the national coverage of the magnetics data displayed in the Virtual Geophysics Laboratory, and then this is our new data set that we just generated on top. So that's the difference between, that's that data set that we took ages to generate, refined, built. This one we generated in a couple of minutes, directly from the same data. So now I hand over the challenge back to Pete. We'll give you some access to the NCI, and he can now see whether he can generate the next magnetic map of Australia directly from that line data. Because I'm not working as a geophysicist anymore. So maximising the value of the National Geophysical Collection. So the National Geophysical Collection of all the sub-collections of magnetics, radiometrics and gravity are now accessible from anywhere via the web services delivered from the National Computational Infrastructure NERDIC platform. They're directly accessible in a high-performance data format for compute directly at the NCI, which Geoscience Australia uses them, and this will enable national-scale gridding and inversions, and who knows, into the future from our national-scale products off the geophysical data. But they're also available for use on the Australian National Virtual Geophysics Laboratory to leverage open-source software codes, or like I've demonstrated here, through your own Python workflows that can be built in Jupyter Notebooks. Good data management and rich metadata were essential to enable this work. There was a lot of hard work done to get that metadata right to enable us to do this. Collaborations across organisations, across GA and across scientific domains made this possible. We had to listen to each other, we had to understand where everyone was coming from to enable to make it work. Improving data interoperability in this way will help break down the silos and drive exciting new transdisciplinary science. If we can work together, if we can work out what the foundations are, now who knows what we're going to be able to do. But change is hard, right? So we can make it easier. If we do that hard work on our metadata, if we get those structures right, if we get the semantics right, if we get the data models right, then it's amazing what we can do. But sometimes we're going to have to put some of the really fun stuff aside to enable us to do that, and then who knows what we're going to be able to do that's going to be fun and exciting and innovative into the future. Thank you, and I'd like to thank everyone that was involved. It was a massive collaboration. I'm just the champion and the communicator, but it was a massive amount of work from across a number of organisations. Thank you.